All right, lesson 2 for Algebra 2. We're talking about multiplying polynomials today. So to start out with multiplying polynomials, we can sort of compare it to finding area of rectangles and squares. So if we were to discuss multiplying 28 times 27, we could do that. We get the calculator out, we could do some multiplication, multi-step, carrying numbers, or we can use what's called an area model. So we would use, split it up into 28 is the same as 20 plus 8, and 27 is the same as 20 plus 7. I can draw a rectangle and split it into numbers or shapes. So this part would be like a 20, and over here we have 8. And this would be like the 20, and that would be 7. So I could count out all the squares that we make. Remember when we did area back when you guys were young? We could count the number of squares in each rectangle. Here we have, let's get a different color. I would have 400 little squares, which is the same as 20 times 20. Here, I would have 160 squares, 56 squares, and 140 squares. So it's just like 400 plus 160 plus 140 plus 56. And that gives me 756. So that's sort of like the area of things. So I can make another rectangle. And we can talk about the multiplication of something of that shape is the same as AB. So we have A plus B times C plus D. It's the same as AC plus BC plus AD plus BD. Correct? So we could add all those together. AC, BC, AD, and BD. But we do need to remember that A, comma, B, comma, C, D are all real numbers. Okay, we're going to use this page as we move on through the lesson today. So, example 1. How is 8 plus 7 similar to 28 times 27? Okay, we're going to use that tabular method. Basically, we need to replace that x with the number 20. 20 plus 8 times 20 plus 7, right? And this is what we just did. But pause there for a second. Okay, can the x stand for a negative number? Okay, can x stand for a negative number? When we're just multiplying, yes. But if we're talking about lengths and areas, those are always positive. So the area model only works when x is greater than 0. Okay? The tabular method we're talking about, it's just a visual representation, not really area. Okay? It's just that visual representation. So, okay, we did this on the previous slide. So now we're sort of doing the same thing. We have an x plus 8 and an x plus 7. Okay, we're going to multiply. Okay, I just multiplied x times x and put it right there. Now we have 8x. Sorry, we're going to keep that in the same color. 8x. 8 times 7 is 56. See how I just multiplied 8 times 7, got 56. 8 times x, got 8x. Now what am I going to put down there? And you can go in any order you want. Now I'm just going to add up everything that's in the box. X squared plus 8x plus 7x plus 56. I really just went in a circle. X squared plus 8x plus 7x plus 56. Not really a circle, sorry. I went in order. So do some addition. I have x squared, 8 plus 7, 15x plus 56. I just multiplied two polynomials. Way to go! Okay, continuing on with example 1. How can we multiply these binomials without using a table? And as we go through it, I'm hoping you'll recognize what the method is called. So let's write down the problem again. X plus, I think it was 8 times x plus 7. So what I'm going to do, I'm going to group these together and use them like that. So I have x plus 8 times x and x plus 8 times 7. And if you remember, that was grouped in a box. So if you like to see that visually, that's what I just did. Now, let's do a little bit more. And I have, I'm going to go right down here, x squared, 8x, and then we're going to do the same thing, 7x, 56, x squared, 15x, 56. So what's that method called? Hopefully you remember, distributive method. So you can use the tabular method or the distributive method. Okay, use the area model to find 16 times 19. Okay, you can try through this or you can skip to the next problem. This is just like a review. So I'm going to go ahead and do this on my own. You're going to push pause now and just try these. You know, sketch it out in your class worksheet that I've already handed to you, but go ahead and push pause. Okay, I'm assuming this is what you got for both examples. Okay, for this first one, area method, which looks just like the tabular method, I've split up 16 times 19 into 10 plus 6 and 10 plus 9. Then if you look down here, it's the same problem, except instead of 10, I have x. So I'm going to go ahead and test my answer down here. I'm going to plug in 10 for my x and do some addition. So I have 100 plus 150 plus 50, 54. I will make math mistakes, not on purpose, and they're usually pretty silly. So if I add these together, I get 304. Awesome. All right, exercises 1 and 2. Use the tabular method to multiply those polynomials and combine like terms. I'm going to work through this one with you, and then you can go ahead and skip ahead if you've got it. My tabular method, it's going to get just a little more crowded on the video. Okay, now I need a table with 3 rows and columns. I'm going to go ahead and fill in x squared, 3x. Now if it's a positive number, I just always keep those plain. You know, I don't need to write the positive on there. If if it's a negative number, you need to carry that negative on through. Okay, now I'm going to go ahead into this block, multiply the x squared and the x squared. That gives me x to the fourth. Next, I'll multiply 3x and x squared. 3x cubed. Okay, 1 times x squared. Then I'm moving down to the next row. X squared and negative 5x gives me a negative 5x cubed. 3x and negative 5 is negative 15x squared. 1 and negative 5x, got it. 2, oh, I messed up my pattern. 2x squared. 3x and 2 is 6x, and 1 times 2 is 2. Now, if you look at this pattern here, as long as I have, to the second power, to the first power, and a constant, second power, first power, and constant, my pattern's going to work out perfectly. In this diagonal right here, I have an x to the fourth. Here, they're all cubes, all squares, and all to the first power and my constant. So I can literally add down my diagonals and I would be done. So let's go ahead and do that. So if I go down this diagonal, I get x to the fourth. I'm adding now. Negative 5 and positive 3 gives me a negative 2x to the third. Negative 15, positive 1, hold on. Negative 15, positive 1, and positive 2 gives me a negative 12. X squared. Okay, the next diagonal here just gives me a positive x and a 2. Now I can just travel on the outside of my tabular method and I just collected all like terms, which is very exciting. So my answer is x to the fourth, not plus. So x to the fourth minus 2x cubed minus 12x squared plus x plus 2. Got it. What I like about the tabular method is it's harder to make mistakes. Okay, you collect everything, it's all organized in a table, you can find all your numbers, and like I said, it's just harder to make mistakes. Okay, you go ahead and try this one on your own, and I'm going to point out one thing, and I'm hoping you will figure it out. I have x squared, x to the first power, and a constant. X squared, no x to the first power, and a constant. You can do one of two things. You can leave a blank for the x to the first power and just put a 0 there, or you're just going to have to work harder to collect all your like terms because they will not be very pretty in a diagonal form for you. I'm going to push pause though. I went ahead and decided to write my 0x in, but notice that gave me all zeros along this row, and when I added up the diagonal, it just kept everything very organized. You don't have to do that. It's totally up to you. All right. If you need more practice, you can go ahead and work through these. But if you feel pretty confident, I would like you to write the answer down, or once you see my answer, write it into your classwork. But if you've got it, I don't need you to practice just to practice. But I'm going to go ahead and push pause and just write the answer in for you. And if you're wondering how I got the answer, please stop me in class. Please go ahead and write these down in your classwork. This is actually a very important pattern that we're learning. Here we have the multiplication of two polynomials that are the same with a minus and a plus in between them. And that's always the answer we get. This is called the difference of two squares. X squared is a perfect square and 1 is a perfect square. So I have the difference of two squares. Here I have the difference of two cubes. Perfect cube, and what it works out to. And then obviously you see here, okay, and what it works out to. So these are patterns that we're going to need to recognize as time goes on, okay? So if you see here, x minus 1 times x plus 1 gives me x squared minus 1. X minus 1 times x squared plus x plus 1 gives me that x cubed minus 1. X minus 1, constant, there's my pattern here. These are all the same. Times x to the third squared to the first constant. X to the fourth minus 1. So the one we just finished on the next slide was x minus 1 times x to the fifth, x to the fourth, x to the third, x squared, x, and 1. All of these cancel out. Oh, wait. Erase that. I went one by one too many, didn't I? Let's make sure we get it right. We started with the fourth. So let me rewrite that. Okay. All of these canceled out and we're left with x to the fifth minus 1. So if we notice, it's our highest degree, it goes up by 1. Okay, our highest degree goes up by 1. Highest degree. See? Do you see the pattern? Example 2 continued. So multiply these polynomials using a table. Now we need to generalize the pattern that emerges by writing down an identity for x minus 1 times anything. It's always going to be x to the n plus x to the n minus 1, etc., until you get down to the constant. Okay, so I'm going to go ahead and do this one, but I'm going to work out the math and just push pause for a second. All right, if you look at this, you'll see the pattern where I have x to the fifth, x to the fourth cancel, x to the third cancel, x squared, x to the first, and minus 1. That's my answer. Okay, I'm going to go back to the previous slide. So we're looking for generalize the pattern that emerges by writing down an identity. Okay, and our identity is going to have letters in it. Pretty basic. This gives us x to the n plus 1 minus 1. That is the answer we're looking for. So anytime we have something of this pattern, okay, that down there will be our answer. Notice when we're doing x minus 1 times a long polynomial, our leading term gives us our answer. So if this was to the 6th power, our answer would be x to the 7 minus 1, etc. All right. So I've got exercise 3 on the next slide, but prior to that, I want to multiply these polynomials together. Okay, I'm going to form a pattern. We just talked about this one, except we had x minus 1 times x plus 1. So can you make a conjecture about the form of the answer? Okay, what's this going to look like using what we learned in the past few slides? So we just did x minus 1 times x plus 1 gives us a pattern of x squared minus 1. Okay, here we can use the pattern from the previous slides. We did x minus 1 times x squared plus x plus 1, and that gave us x to the cubed minus 1. But now we have a y there. So now we're trying to figure out what to do when our terms are not so simple. Sorry, we're going to go ahead and do this. I'm going to do the distributive method though. Okay, just distribute through. And I'm writing in blue now. So the first term multiplied through gives me, and then I have a negative y multiplying through. Negative y times x is negative xy. And then multiply there, negative y squared. Middle terms cancel out again, and we're x squared minus y squared. Just like x minus 1 times x plus 1 gives me the first term squared minus the second term squared, because 1 squared is 1. Here we're going to have the same thing. I'm just going to, with the one we just did, with this example right here, I bet you guys can figure out this example right here. So our first polynomial, x minus y, which is just like x minus 1, and our second polynomial. So our answer is going to be the first term cubed minus the second term cubed. So it's going to be x cubed minus y cubed. But let's move on to something harder. All right, multiply it out using the distributive property and combine like terms. So first, I'm going to grab this x and multiply it to every single term that you see. Can you guys make a conjecture of what my final answer is going to be while I do this? Let me erase that. It's sort of sloppy. So I'll talk through it. First is going to be x to the 4th plus x cubed y plus x squared y squared plus xy cubed. Now I'm going to grab the negative y and multiply it through. Distribute it. So minus x cubed y minus x squared y squared, need a new line, minus xy cubed minus y to the 4th. Now we're going to cancel out things that cancel out. I have positive x cubed y, negative x cubed y, positive x squared y squared, negative x squared y squared, positive xy cubed, negative xy cubed. And look what I'm left with. X to the 4th minus y to the 4th. Pretty simple. Sweet. All right. Oh, this did not get edited correctly. I do apologize, and I can't fix it now. All of these are supposed to be exponents. I do apologize. I will occasionally make mistakes, and sometimes I can fix it. But at this point, it is 10:17 in an evening, and I can't fix it right now. But yeah, if you guys just follow along, it'll be fantastic. But really, what I want you to do is investigate the pattern found in expanding these expressions. Okay, look for the pattern. We're going to use the distributive method. I have x squared. I'll write this first one out for you. X squared plus y squared times x squared minus y squared. That's a squared. Okay, let's go ahead and try to multiply it. But I'm going to erase that because it got really messy. Okay, before I move on though, notice my patterns. X squared plus y squared, x squared minus y squared, x cubed plus y cubed, x cubed minus y cubed. Let's see if we can find a pattern. Okay, first term, second term gives me x to the 4th power plus x squared y squared, and that is incorrect. That should be minus. Now multiply the second term. Second term. y squared times x squared will be plus x squared y squared. I'm sorry, I'm in black now. And then minus y to the 4th power. Notice these two cancel out, and I have an answer. I'm going to do this next one, and then we're just going to make conjectures of the last two. So let's go ahead and distribute. First term, second term, I have x to the 6th minus x cubed, y cubed, plus, multiply those through, x cubed, y cubed, sorry about that, minus y to the 6th. Cancel out, and I'm left with x to the 6th minus y to the 6th. So what do you guys think we're going to have here? Okay, if we look at the pattern, I have x squared plus y squared, x squared minus y squared. The middle terms always cancel out, and I'm left with the first term squared and the second term squared. Actually, the first term times itself, not squared. So the first term times itself, and the second term times itself. Here, same thing, x cubed times x cubed, y cubed times y cubed. So this last one we're going to have, I'm going to guess x to the 8th, the middle terms are going to cancel, minus y to the 8th. And here, x to the 5th times x to the 5th is x to the 10th, minus y to the 10th. Perfect. Let's see how we can use this. With every term, we did 2 times the exponent. Okay, it's to the 3rd power, to the 6th power, 2 times the exponent, to the 4th power, to the 8th power, 5th power, 10th power. So that's going to be our generalization. So now we're going to multiply using the distributive property, which we just did, and combine like terms. And when we did that, we got x to the 4th minus y to the 4th. But we want to generalize the pattern that emerges and write down an identity for any positive integers n. So our identity, if we look, and you can look at the previous slide, hold on, that's going to be our pattern, okay? X to the n minus y to the n times x to the n plus y to the n gives us x to the 2n minus y to the 2n. That is our identity for that form of problem. In closing, let's write down 2 important ideas from the lesson. Okay, first of all, we learned about multiplication of 2 polynomials. It's performed by repeatedly applying the distributive property and combining like terms. So, a multiplication of 2 polynomials is repeated distribution and combining like terms. Okay, and we also learned about some identities. IES. Identities, let me get a fresh slide so we can look at it. We did A plus B times C plus D. We did distributive property. Okay. Next we did A plus B squared. I don't think I spelled this one out quite as clear though. These are identities that if you can memorize them for Algebra 2 or recognize them quickly, it'll make your life easier. very cool. And this one sort of includes a few special ones where we did x minus y, x plus y gives us x squared minus y squared. And then we did x squared minus y squared times x squared plus y squared. X to the fourth minus y to the fourth was sort of the fun one. And then lastly, sorry, those were the two special under there. X minus 1, x to the n plus x to the n minus 1 plus dot 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 x squared x plus 1. And that simply gave us x to the n plus 1 minus 1. Those were the identities. That's all I have for today. Good work.